Okay, so we're back this week and we'll be looking at nonlinear models and how to do them in R. So as usual, first step is we're going to import our data, and we're going to start this week with a little data exploration. We have two continuous variables, and we want to know, is there any curvilinear pattern between the X and Y that we might want to model? So ggplot2 is a really powerful library, and we've used that in the past to make graphics. So we're going to be using that again today. And I'm making very, very minimum plots. If there is so much support for ggplot online, you can make scatter plots, change the colors and everything pretty easily. So the first thing we do in ggplot is the first line is always ggplot, the data set goes next. And then this is aesthetics. I want to add a Y and an X. So my X will be teacher pay, my Y will be SAT verbal scores. Then I want to add points, like a scatter plot. And then I want to add a regression line. And in ggplot, the relevant command is geom smooth. And I'm going to use a method called a linear model to add a linear line. So I'm going to store this ggplot object in plot1. You can see it's created my environment over there. I can call plot1. And there you have it. So that's just a really bare bones regression plot. And you can change the X title, X label, Y label titles. You can add a title, center the title, change the increments, add grid lines. There's so much customizability. Really, whatever you do just is a few minutes away through a Google search. Okay, so another thing I might want to do is remove that standard error line. I usually do that. I find it kind of annoying that it's like that by default. So there you have it. Same plot, just no standard error. Now I can look at plot 3, and here I can add a smooth regression line, again called a LOES. We saw this in SPSS, and you can see there's some evidence of curvilinear relationship there. And then finally, I can also add a quadratic model, what that would look like. And so I want to know, this is a little confusing. So you have to use the formula argument in the geom smooth wrapper function. And here, Y is going to correspond to what you put up here, and X is going to correspond to teacher pay up there. And I'm adding the squared version. You'll see the syntax below. So I parentheses X squared, that's how you add a squared version of X using the basically syntax in R. And we'll cover this below, so that might be a little strange for now, but hopefully by the end of today's video, you'll feel comfortable with that syntax. So now I'm going to run plot 4, and there you can see it's added a smoothed quadratic line. And these little arrows kind of useful. You can cycle forward back. Now let's say I want to save one or two of these figures. Well, if I go to my figures and you can see it's empty. When I specify figures // I'm telling it to save it in the figures folder. Remember, you have to be loaded in the project for this to work. And you can see they both added there, and I can come here and you can click on them, and there's your figures and whatever dimensions and specifications you created them with. Okay. So, these these scatter plots are really helpful, right? Now, their big limitation is that often I have other variables in my model. So this is the raw association between teacher pay and SAT verbal scores, ignoring everything else. Of course, an issue is when you use a regression framework, you need to control for other things. And so really the question becomes, is the association between SAT verbal and teacher pay quadratic after I've accounted for the other variables? And so that's what we use partial plots for. So there's this library called the cars package. And again, if you don't have this stuff, remember you have to install .packages and then do it like that. I'll run that. I already have it installed, and when you run this again, it basically just updates it and reinstalls it. So, it'll do its magic. Hopefully you get these successfully successfully installed messages. And then you have to call library to tell R, hey, I want to use this package was written by some other author somewhere in the world. And now I'm going to create a mod 0, which is going to be just the linear effects of teacher pay and percent taking. So no quadratic regression yet. I save that in mod 0. And now there's a function in the cars package called CR plots. So I just call that, and just like that, I can hit the zoom there. You can see there is some evidence of nonlinearity. I would say more so for percent taking. So that's how we do partial plots. Pretty simple then. Now there's two easy ways to do polynomial regression. You can make your squared terms. So I'm making teacher pay squared, which is just teacher pay times teacher pay. Of course, to make a cubic version, I'm going to do it 3 times, multiply it by itself 3 times. And then percent taking, I can also make a squared. So I've added 3 new variables to my data set, and you can see they're there on the end, my environment. Now, the principal marginality says if I want a cubic term, I need the squared and linear term. And here I want a squared term of percent taking, so I want to use percent taking. So this is polynomial regression. And you can see it's that easy. The interpretation is a little tricky, which we covered in the lecture, but estimating it is really not difficult. Now there's a second way you can use special R syntax, which I was saying above. It's this little I, and then here I'm going to square teacher pay and then cube teacher pay, and it's going to give me the same model. So you can compare them, you'll see they're the same, doesn't really matter. Now, an issue, of course, is collinearity. Hold on, is that what's next? Okay, right, hold on. Before I get there, let me step back. So does adding these extra nonlinear terms explain a significant amount of additional variation in Y? Well, look, I saved these in a mod, the one with the full nonlinear terms, and then mod 0 is still mod 0 from above, where I had only linear terms. So I can, of course, do an incremental F test. And there, the test will tell me, yes, there are some nonlinearities, at least for one of these variables, that we should include. It doesn't tell us where, right? If you want to know where, you got to really come here, and you can see really percent taking, which you can see in the partial plot, is really where the nonlinear term exists. Again, though, if you remove this cubic term, you might see movement on the teacher pay squared. Okay, so, but an issue that we want to deal with, let's see, is that these are going to be highly collinear. And so what that means is they're really correlated. And so as teacher pay squared goes up, well, so does teacher pay cubed, and so does teacher pay. And as they move together, it's really hard. We're asking too much of our model to kind of pull apart those effects because they're too highly correlated. So how we deal with that is we're going to center the variable. There's a really useful function in R called the scale function. It centers and standardizes. Remember, standardize means you divide by the standard deviation. That's going to make the range go from like -3 to 3, for example, if you're centered. And then centering just means make the mean 0. So I don't want to standardize. I could, but I don't want to here. I want to just center. So the default is to standardize. So I come in here and I tell R, actually, no, I want to not standardize the data. And the default for center is true, so I don't even have to specify that here. So I'm going to make a new variable, teacher pay underscore C, very common naming convention for centered data. And I'm going to use the scale function on teacher pay itself. I'm not going to standardize it. And so, when I run the summary, the scores are not between -3 and 3 because it's not standardized. It goes up to 14, has a minimum of -10 almost. But the mean is 0. And that's what we mean when we say center a variable. So, okay, that's how we create centered data. Now, I want to first, before I go further, I want to look at the extent of the problem when we have uncentered data. So there's a correlation function, and I'm going to feed into the correlation function the original squared and cubic terms. And when I do that, look at how highly teacher pay is correlated with teacher pay squared and teacher pay cubed. Shouldn't be surprising. You look at percent taking, it's the same thing. So we need to resolve that issue, right? And we do that with centering. So I'm going to create a center squared, which is literally just the centered version times the centered version, and so forth. And I'm going to re-examine this correlation matrix. Looks like I forgot to do something. Which one is having an error? Okay. Replacement has 0 rows. Why does it have 0 rows? Because I forgot to define percent taking centered. That's why. So let me see. Before I run this, I need to, of course, create percent taking squared. Sorry, centered. And so I just got to run the scale function there. What's going on? That percent taking, this doesn't want to work. I think I might have percent taking is still good. Oh, right, because percent taking didn't exist. So now I have the correct variable in there. Now it's going to create my new variable. Now I can look at the correlation and look, the correlation much weaker, you know, still strong, but it's manageable now. Collinearity, it's not a matter of if, it's a matter of degree. When the correlations are above 0.9, we typically are in a situation we call extreme multicollinearity, and we want to avoid that wherever we can. And so this is how we get around it with nonlinear models. We center and then use the centered versions to make squared or cubic terms. Okay, so well, we have our centered version, so we can go ahead and add them like this. And you should see the coefficient estimates are the same as before. The standard errors are going to be a lot lower. So let's go ahead and look at that stuff. So this is before. Model fit and everything should be the same. So if you look at model fit 89 point, that's the same. P-value there is the same. R squared, the same. And then if you look at the coefficient estimates, they're actually different. It's not what I was expecting. Let me think about that. Yes, they should be different, of course, yeah. So they should be different actually, because you know, when I don't center, like, so take the linear term here. That's the slope when x is 0. But if I make the mean, if I make this the new mean by centering the variable, the slope is actually going to be different at that point. So actually they should be different. That's right. Okay. So in any case, you can see though the model fit and everything, that's really unchanged. Right. So it looks like, you know, the squareds and the biggest terms are unchanged, but the other ones do change. Okay. So in any case, getting back to our running of these regression models. So that's how to use the centered version. And then, you know, we also talked about transformations. I don't recommend you do them too often, but you can go ahead and just transform X right in there. You can create a new column. So here I'm just using a squared quadratic effect for X. And then here I'm going to log percent taking. And, you know, R is happy to allow you to do it that way. So you can actually see teacher pay squared does have an association. The reason I don't like transformations as much, the log one is actually pretty nice. But, you know, you'll see in the literature when they're using log, it's always very obvious. But this is kind of confusing. For every 1 unit rise in teacher pay squared, y is changing by this amount. It's kind of hard to interpret. The same with the log, but there are some cases where logs will make it easier, because log really becomes more about the magnitude than like a 1 unit increase. It's about like every time you square the variable. And so sometimes the squared relationship or the square root relationship could matter. And you'll see, like, if you read some more advanced text, especially in economics, they use logarithms a lot because it can make the interpretation easier. But anyways, for most of us, we're not gonna have to worry about that. Transformation, the literature will make the decision for you. If they use log population, go ahead and throw log population in. And then look at how they interpret it. So that's my suggestion there. Okay, so that's all for today. Thanks for joining in, guys.